Hello and welcome to the tutorial where I'll teach you how to use very large datasets with PyMINEr. Now, the dataset included in this example is just the same dataset that we used before, which is not a gargantuan dataset, but it'll act as a proof of principle. So if you haven't already, stop and download the two files linked in the description below, where it'll be the input file, and then later on we'll use the genes of interest file so that we can highlight some interesting genes. Alright, once you've done that, I'll show you a little bit how to convert a typical input file, which is a tab delimited text file, as is the format of the file that you just downloaded, and convert that into a format which can handle data sets of unlimited size, or at least limited only by the size of your hard drive. So once you have your data set downloaded here, we'll go over to the terminal, and the command for converting your file is tab to h5.py, and if we just type in -h to look at the help section, we'll see that really all you need is that command, tab to h5.py, and then you just drag and drop the input file that you have. So let's give that a whirl. And just drag and drop your file over here, and click enter, and now it's doing the conversion. And what this is going to generate is three files. It will be your actual data file here, which is airway merged -hdf5, and then it also creates your ID list, which contains the first column from your airway merged input file, which is just going to be the ensemble IDs, and then the other file is the column IDs. So in the case of single cell RNA-seq, this is going to be the cell identifiers that is going to be in a typical data set stored in the first row, where each column corresponds to the ID of the cell. So to run PyMINEr using this file, what we need to do is type PyMINEr.py, and then when you're using a large dataset file, the HDF5 format, what you need to do is type the HDF5 there, and this tells PyMINEr that you're not using a tab delimited text file, you're using this converted file format. And then similar to before, you put the -i for the input file, and then drag and drop your input file there, and then type IDs, and then drag and drop your ID list here, and then your columns with the command calls, and then drag and drop this here. And then the last thing I'm going to show you is how to use genes of interest. So from the previous tutorial, we saw the high expression marker genes file, and what I've done here is for each group I've copied the top five marker genes for each of those groups. And in the left column here we have the ensemble gene IDs, and then in the right column is the gene symbols. All you really need is your first column here, but you can type in whatever you want here, and this is the ID that's going to show up in your heat map. So if you want something that you can use in a publication right away, all you'll have to do is have this second column here, and PyMINEr will update that in the heat map. And again, this is a tab delimited text file where you have just a single tab delimiting your first column from your second column. And what you can also do is just make this up in Excel, open up a text file, and then copy and paste it into the text file, and it automatically defaults to using a tab delimited format. But if you're doing that, be careful, because sometimes the Excel will also copy in a new line at the bottom, and just make sure to remember to delete that so that you don't have an empty column at the bottom. So once you're ready with that, the genes of interest argument is GOI, genes of interest, and then drag and drop that over here. And then, like before, because this is a mouse data set, don't forget to add the species argument. And then click go. So once you've finished the PyMINEr run, the results will look like this. And you'll notice here that there's a new tab that wasn't there before called genes of interest. These are the results of your genes of interest. So this is what the heat map looks like, and you can see that there's pretty good separation of all of your different groups, as you might expect. And the other output from using genes of interest is the shortest path of all genes away from your genes of interest. So if we have a look at this in Excel, go to downloads. So here along the first column are all of the genes in your data set, and then how far away they are from each of your genes of interest. And what this allows you to do is to look at the structure of the network graph that was built from your data set, which is here. And say you have a gene somewhere here in your network graph. If it's very close, if a gene in the genome is very close to that gene, it'll be in this general vicinity on the visual display of the expression graph, and its degree of separation will be very low. And that can tell you interesting things about transcriptional relationships, as a paper that I'm currently working on will show that the closer a gene is to another gene, the more likely they are to have a direct regulatory relationship on one another, at least in the case of transcription factors. There are other different aspects of co-expression graphs which can be very useful in other ways. It's particularly useful for integrating data sets, where you can essentially boil down the expression relationships that two genes have with each other to a single number of how far away they are in an expression graph. And then you can integrate that with whether or not a gene is a SNP with a given associated risk for a specific disease you're interested in, or lots of other different data sets that you can integrate just by having a single number here that is going to correspond to how well a gene is correlated to your given gene of interest. And that's the long and short of using both the HDF5 file format as well as using the genes of interest option in PyMINEr. Thanks for watching.